Basic derivatives. Let's start with an example. Y equals x squared. Okay, to solve this, you will need the power rule. The power rule is y equals x to the power of n. The derivative is n x to the power of n take 1, which basically means bring down the n, multiply it, and minus 1 off the power. Okay, so if we do the derivative of this, we perform the derivative of this, it will be bring the 2 down and multiply it by x, and then take the power and subtract 1. Okay, so we can simplify this by saying 2x to the power of 1. You can keep the power there, or you can leave it off, whatever works for you. It means the same thing, 1 or no 1. And for the second derivative, we will having a number at the front won't affect the power rule at all. It just means that whatever power you have, when you bring it down, you'll have to multiply it by the number that's there, as well as multiplying it by the x. And then, I'll explain. So bring the 1 down, so it's 1 times 2 times x to the power of 1, take 1 from here. Simplify that further. You have 1 times 2 is 2 times x to the power of 0, because 1 take 1 is 0. Okay, so when you have x to the power of 0, that equals 1, just like 1 to the power of 0 equals 1. Okay, so simplify that even further, and you are left with just 2, because 2 times 1 is 2. Okay, so explaining, I'll do a few more examples, but to explain notations that you might come across, there are 2 general proper notations that you might use, and then there's Newton's, which is very unused, and then there is one that a lot of mathematicians use just because it's easy. Okay, so the first proper notation is one by Leibniz, a bloke called Leibniz, and he does them. Let's say you've got your letter, and then your letter or your function, your letter to which equals the function. You derive that, and you will multiply it by the differential operator. Now the differential operator, well that just equals dy over dx. But the differential operator, this here, equals it's just saying that you're multiplying the function with respect to x. Like you're multiplying by the function with respect to x, which is, or you're deriving the function with respect to x. So if you change the function, let's say the letter you're using for the function wasn't y, it was g, and that equaled, say, u squared. Instead of using y and x, we're using g and u. The differential operator for this would look like dg over du, because you're deriving the function with respect to the variable, which is g with respect to u. Okay. And so if we were to derive, back up to here, if we would derive this again, we would be multiplying again by the differential operator. So that would be d over dx multiplied by d over dx multiplied by y. Okay, that would give us d squared multiplied by y over dx squared. Okay, so when you're following this type of notation, whenever you keep proceeding through, once after this and you've reached here, you just add 1 to the power. You just add 1 to the powers as the powers are shown here. Once you do it enough, it'll just be like second nature. And the second proper notation is one by Lagrangians Notation. So it's Lagrange. I don't know if I'm pronouncing that right, but it looks like it. So he does a process sort of. Let's do that as an example. So he's got, it's sort of like the function. That's the function there. That's the same as y. So y would equal that. But yeah, you understand. So the function equals x to the power of 2. If we were to derive this function, the notation would look like f dash x, which is saying f, which is the first derivative, but it's f dash and it's respect to x. So it's the function with respect to x, which would be 2x, the derivative. To derive that again, you would f dash dash x, which equals 2. And so you just keep adding dashes. Some people add Roman numerals, because when you get up to big numbers, having a x up the top for the 10th derivative, not like you would get there. It's very unlikely, but it's a lot easier to have instead of dashes. But yes, that's dashes is what's used in his notation. And then Newton's notation is, I'll number these. Newton's notation is simply y, like the function, the letter of the function, and then when you derive it, he just simply puts a dot. And then he derives it again, puts a dot dot to know how far he's gone through. And for the fourth, which is just way I've seen a lot of people do it, and it just seems to catch on because it's very easy, and not like this is hard, but you basically start off with your letter of your function, and when you derive it, you put the letter and a dash, and derive it again, a letter and a dash and a dash. Basically, it's a mixture of Newton's and Lagrangian's way, and basically it's no different. It's just about as easy as that, but for some reason the dashes seem to catch on easier. So that's the most common way you'll see me do it, just because it's force of habit. Okay, for the examples. Okay, so we'll start off with example 1. We'll do y equals 2x to the power of 3. Okay, I'll write the power rule over here. Basically, same process as before. Number doesn't matter to the power rule operation. You just multiply the power by the number at the front. Hope that makes sense. So y dash equals 3 multiplied by 2, which is 6. X, 3 take 1, which is 2. So the first, the 6x to the power of 2 is the first derivative of 2x to the power of 3. Okay, so example 2. Y equals 6x to the power of 6 plus 3x to the power of 9. Okay, so this process, it doesn't make any difference because if you were to multiply the two variables, you would use something called the product rule, but because it's just the plus, I'll explain that in a further video, but because it's just the plus between the variables, you use the power rule. You treat it as separate issues. Okay, so y dash equals the first one, which would be 6, you bring that down, the power rule, so it's 36, x, 6 take 1, is 5, plus, then you focus on this one, which would be 9, you bring that down, multiply by 3, and then that'd be 27, x, 9 take 1, 8. And then that's the first, that there is the first derivative of this up here. So, third example, and final example of this lesson will be example 3, will be y equals square root of x. And that isn't anything big. Oh, I'll bring it down. That isn't anything big, it's just x to the power of a half. And you still treat that as the power rule. You bring it down and you take 1 off the power. So, y dash 1 over 2 multiplied by x to the power of half, take 1. Okay, so if you don't know, half take 1 is the same as a half take 2 over 2, because that's a whole, which is negative 1 over 2, because 1 take 2 is negative 1 over 2. Okay, so put that in, 1 over 2 x to the power of negative half. Okay, so in case you don't know, when you have x to the power of a negative, let's say negative 1, that will equal the same as 1 over x to the power of 1. And when you have 1 over x to the power of negative 1, that will equal the same as x to the power of 1. So if we implement that over here, that's 1 over 2 multiplied by x half over 1. If we follow that through again, that is 1 over, if we multiply that together and simplify it further, that's 2x to the power of a half. Simplify it even further, 1 over 2 square root of x. Thank you for watching.